Find the exact area of the region that lies above the x-axis and below the curve, given by the parametric equations x equals t squared plus 4t plus 9 and y equals e to the power of negative t over the interval where t is greater than or equal to 0 and less than or equal to 1. I've already graphed the curve on the right here in red from t equals 0 to t equals 1. Our goal is to find this bounded region here. If we have a non-self-intersecting plane curve above the x-axis, then the area under the curve bounded by the x-axis over a given interval of t equals the integral from a to b of y of t times x prime of t dt, which means in our case the bounded area A equals the integral from t equals 0 to t equals 1 of y of t, which is e to the power of negative t, times x prime of t, which is the derivative of t squared plus 4t plus 9 with respect to t, which is 2t plus 4 dt. Let's go ahead and distribute and write the integrand function as 4 e to the negative t plus 2t e to the negative t. To integrate 4 e to the negative t, we need to perform substitution, and to integrate 2t times e to the negative t, we need to apply integration by parts, as well as substitution. Let's consider the antiderivatives below, so we'll temporarily leave off the limits of integration. Let's first consider the integral of 4 e to the negative t dt. Performing substitution, we have u equals negative t, and therefore du equals negative 1 times dt, or negative dt. Solving for dt, we have negative du equals dt. Writing the integral with respect to u, we have 4 e to the u, but then dt is equal to negative du. The antiderivative is negative 4 e to the u plus c, or negative 4 e to the negative t plus c. And now let's find the antiderivative of 2t e to the negative t. Again, this first requires integration by parts. If you need to review, the formula is here below. We have u equals 2t, and therefore dv must equal e to the negative t dt. And now we differentiate to find du. du equals 2 dt, and we integrate to find v. Integrating both sides of the equation, again, we need to perform substitution on the right, which is similar to our work shown here on the left. V equals negative e to the negative t, again after performing substitution. And now applying the integration by parts formula, the given integral equals u times v. Let's write u times v as negative 2t e to the negative t, and then minus the integral of v du. Because v is negative, we can change this to addition, and then we have the integral of 2 e to the negative t dt. And now this integral also requires substitution, just like we performed substitution here on the left. The final antiderivative is negative 2t e to the negative t minus 2 e to the negative t plus c. So now going back to the original problem, we now know the antiderivative is equal to the sum of these two antiderivatives. And notice we do have two like terms. Negative 4 e to the negative t minus 2 e to the negative t is negative 6 e to the negative t. So the antiderivative is negative 6 e to the negative t, and then minus 2t e to the negative t. And now we determine big F of 1 minus big F of 0. For big F of 1, we substitute 1 for t, which gives us negative 6 e to the negative 1 minus 2 times 1 times e to the negative 1 minus, for big F of 0, we substitute 0 for t, which gives us negative 6 e to the negative 0, or just 0, minus 2 times 0 times e to the negative 0. Of course, this term has a factor of 0, so that's 0. Let's write negative 6 e to the negative 1 as negative 6 divided by e, and then we have minus 2 e to the negative 1, which we can write as 2 divided by e. And then we have minus e to the 0 is 1, so we have minus -6. Simplifying one last time, notice this simplifies to plus 6. Let's write the exact value as 6. And then combining the fractions here, we already have a common denominator. We have minus 8 divided by e. This is the exact area of the bounded region here on the right, which because it is area would be square units. I hope you found this helpful.